Okay, question 3. And Peter's model here state two assumptions she needs to make. Peter needs to make to use her model. She needs to assume that throws are independent of each other. So independence. And she also needs to assume that the probability for each child to hit the target is 0.1. So constant probability of 0.1 for each child. Okay, it's not to do with a consistent number of throws because that's part of the actual setup. So it's not an assumption she needs to make. So using Peter's model, find the probability H is greater than or equal to 4. So the probability that H is greater than or equal to 4 is 1 minus the probability that H is less than or equal to 3. And that is 1 minus 0.9872, which is 0.0128. Okay, for part C, we want to know the probability that F is equal to 5. That means you get 4 misses followed by a success. So that's 0.9 to the power 4. You've got to have those 4 misses followed by a success, which is 0.1, and that comes to 0.06561. Okay. Now, the next part, in part D, we have Thomas assuming that no child will need more than 10 throws. So his model, if we draw a probability distribution for it, it would look something like this, wouldn't it? It would be the number of throws is 1, 2, 3, 4, all the way up to 10, and the probability that F is equal to is 0.01 when A is 0, and then it's 0.01 plus A, or my table's a bit dodgy, and then the next one will be 0.01 plus 2A, and then 0.01 plus 3A. So what we can see is it's 0.01 10 times plus the sum of A from A equals 1 to 9. And all of that must come to 1, because by the time you get to the end, the probability sum must be 1. So I've got 0.1 here. So those two multiply together to make 0.1. And the sum of the integers from 1 to 9 is 45. So, and that's, so 0.1 plus 45a, that's 1a plus 2a plus 3a plus 4a and so on, is equal to 1. So therefore 45a is 0.9. So a is 0.9 divided by 45, which is 1/50th, or 0.02. Part E, the probability that F is equal to 5 under this model. So the probability that F is equal to 5 is 0.01 plus 4/50th. Now we know A is a 50th. Looking at the model, it's 4 lots of A. So that comes to 0.07. So beg your pardon, 0.09. And finally, in F, how the models differ in describing the probability that a dart hits the target. Well, Peter assumes that hitting the target is constant, whereas in Thomas's model, the probability increases. So the significant difference is that in Peter's model, the probability is constant, whereas in Thomas's model, the probability increases with the number of throws. Apologies for the spelling.